Welcome back, students. So yesterday we have discussed SAQs from atom chapter, right? Like what is Bohr's limitations of Bohr's atomic model we discussed. And one more thing we discussed, spectral lines. Explain the different types of spectral lines of hydrogen atom. We discussed Lyman, Balmer, Paschen, Brackett, and P fund, like that. So one more question is there from that chapter, that is this is came on the recent exam also. Write a short notes on de Broglie explanation of second postulate of Bohr second postulate of Bohr, that is quantization of angular momentum. Okay, so that we will discuss now. Okay, write a short note on de Broglie's explanation of Bohr's second postulate of quantization. So see now what is. So question is from atom chapter only, it is SAQ. The question is write a short note on de Broglie's explanation of Bohr's second postulate of quantization. Write a short note on de Broglie's explanation of Bohr's second postulate of quantization. So actually, before the actual part of the question, so little bit we need to know what is de Broglie's, how we explain the second postulate. What is second postulate of Bohr's model? So yesterday I told that there are three postulates. Bohr is given as the atomic model in form of three postulates. In that second postulate is the angular momentum of orbiting electron. Angular momentum of orbiting electron is quantized. So that means they have given that the angular momentum of electron mvr is equal to nh by 2 pi. That is second postulate. So he is giving our explanation for the second postulate of Bohr's. Then according to de Broglie's, every particle has a wave nature. Every particle has wave nature means what? Electron is revolving around the nucleus in a atom. So from the de Broglie, electron also should have wave nature. Electron also has some wave nature. So electron has a wave nature. That means it will emit some waves. Okay. And it has some wavelength. And the wavelength of de Broglie's wavelength of matter wave is, or a particle wave is, lambda is equal to h by p. H by p, where h is a Planck's constant, p is the linear momentum of the particle. So that is de Broglie's wavelength. Then from this de Broglie wavelength, he is trying to explain the second postulate, that is conservation of angular momentum, or quantization of angular momentum is explained. How he explained means this de Broglie's. So he said that an electron is revolving around the nucleus. Nucleus is a center point that has positive charge. An electron is revolving around the nucleus with some velocity v in particular orbit of radius r with the velocity v. So as per this one, from the Bohr second postulate, we can write, you see, from Bohr second postulate. Angular momentum of orbiting electron is quantized. Orbiting electron, angular momentum of orbiting electron is quantized. That means what? From this diagram, this particle has some mass m revolving with a speed v in a particular orbit of radius r. Then the angular momentum, that is L, I can write it as mvr, that is equal to nh by 2 pi. N is 1, 2, 3 and so on, where h is the Planck's constant. R is the radius, v is the velocity, m is the mass of the particle which is orbiting in that particular orbit. Okay, this is second postulate. From this, how this de Broglie explains the second postulate means. So according to that, de Broglie. So from de Broglie, every particle has wave nature. Every particle has wave nature. So every particle has wave nature. Every particle has wave nature, correct? And according to this, according to him, every particle has wave nature, means definitely orbiting electron. Electron is also in a particle. So electron should have wave nature. That means electron also have some wavelength. Then according to this wave nature of electron or wave nature of the particle, and from the de Broglie's, the de Broglie wavelength can be expressed as wavelength lambda is equal to h by p. It is called wavelength of the wave emitted by the particle, or de Broglie wavelength we can say. De Broglie wave length. De Broglie wavelength. In this one, lambda is equal to h by p. H is a Planck constant. P is the linear momentum of the particle, that is m into v. M into v. This is individually second postulate of Bohr's, and this is the wavelength of the de Broglie's for matter wave or particle wave. Lambda is equal to h by mv. Now, how that is connection? How is explained that? Means de Broglie saying that whenever electron revolves around the nucleus in a particular orbit, it emits wave. It emits wave, which is standing wave. That particular wave which emits, and that too is standing wave. Similar to this standing wave which is emitted by the electron while revolving around the nucleus. This standing wave is similar to the standing wave or stationary wave generated on the stretched string. Stationary wave generated in the stretched string. So, in stretched string, how the stationary wave is generated or developed? Very similar to that wave, the electron wave which is emitted while it is revolving around the orbit. That wave is also a stationary wave which is similar to the standing wave produced in a string. So according to him, he is saying that the wave emitted by orbiting electron is a standing wave which is similar to standing wave in a stretched string. Standing wave in a stretched string. The wave which is emitted by the orbiting electron in a particular orbit is standing wave which is similar to the standing wave in a stretched string. But we know in a standing wave in a stretched string, it will form many wavelengths. It can have many wavelengths. But between the two stretched points, between the two fixed points, all are these wavelengths, that is many loops will form. All these many loops or many wavelengths will get, that all wavelengths are lies between two fixed points, that is two nodes. Two nodes. And this will be present. This is possible. That means all this number of wavelengths which are forming on a string between the two nodes will be possible only that the wavelength of different loops emitted in the stationary wave is integral multiple of fundamental wavelength. Integral multiple of fundamental wavelength. I think you remember that LAQ I explained that. That is stationary wave on stretched string. In a stretched string, all types of harmonic will form. Odd and even. 1, 2, 3, 4, all will form. Correct? So very similar to that, here the stationary wave produced on the emitted by the orbiting electron also very similar to the stationary wave emitted in the stationary wave developed in the string. For example, if we take an electron is orbiting in a particular orbit of radius r. Okay. And this wave will generate like this. Like this standing wave will be generate. And this standing wave, many wavelengths will get. Many wavelengths will get. But the total length of the orbit, is equal to integral multiple of wavelength of the standing wave. Integral multiple of wavelength of the standing wave. From this we can write total length of orbit is equal to integral multiple of wavelength. Integral multiple of wavelength means what? That is total orbit length. Orbit length means what? Circumference of the orbit. Circumference of the orbit. Orbit radius we have taken as r. Then circumference of the orbit is how much? 2 pi r. Length of the orbit or length of the circle or length of the total orbit is what? Circumference of the orbit only. So r is the radius, means circumference will be how much or length of the orbit is how much? 2 pi r. Total length of the orbit is equal to integral multiple of wavelength. Integral means n, 1, 2, 3, 4, 5. Into wavelength means lambda. So 2 pi r is equal to n into lambda. N into lambda. Now, in this r is the radius of the orbit, n is the integer value, that is n equal to 1, 2, 3, 4 and so on. But in this lambda is the wavelength emitted by electron. Electron means particle, particle wave means matter wave, matter wave means de Broglie wavelength. De Broglie wavelength means again lambda is equal to h by mv, I can write h by mv. So I replace the lambda as h by mv, you see 2 pi r n into h by mv. Okay. From this, I will take this mv this side 2 pi is this side. MV is this side, 2 pi that side. What will happen? You see from this. R already there. From this MV, I'm taking this side. So this will get MV, R is there. And already NH is there. And denominator we are bringing 2 pi. So NH by 2 pi. MVR is equal to NH by 2 pi. That is L MVR is equal to NH by 2 pi. It's the second postulate of the Bohr. And from the de Broglie's wavelength, also we got orbiting electron as MVR is equal to NH by 2 pi. That means indirectly this is angular momentum of revolving electron. L is equal to NH by 2 pi. This is second postulate of Bohr. So this is in this way, the de Broglie explained the second postulate of Bohr. Clear now? Write a short note on de Broglie's explanation of Bohr's second postulate of quantization. First, we need to define what is second postulate of Bohr. Then after, according to the de Broglie's, every particle has wave nature. The wavelength of the de Broglie's is this much. And from that, whenever orbiting electron revolving in a orbit, it emits a wave as per the de Broglie's. And this wave emitted by the orbiting electron is similar to the standing wave developed in the string. And that multiple waves which are generated on the string is possible only the length of the string is integral multiple of the wavelength. So similarly, a length of the string means length of the orbit. So the length of the orbit is integral multiple of wavelength. So from this we have proved that NH by 2 pi as angular momentum of orbiting electron. Clear now? Is this clear? Student, is it clear? Any doubt? Any doubt on this particular question? You can raise your hand. Okay, no doubt. So next we'll move on to that another chapter of SAQ question. So from the atoms we have studied 3 limitations of Bohr model, different spectral line series, and the second postulate of de Broglie's explanation. Okay. Now moving into the next chapter. Again, SAQs only we are going to be discuss. Tell me. हाँ कराते हैं हमको रे ऑप्टिक्स तक नहीं गया. So next chapter is EMI, electromagnetic induction. Electromagnetic induction. EMI. SAQ from this. So we will going to be discuss 2 questions from this. One is motional EMF. Motional EMF. Another one is advantages of eddy currents. Advantages of eddy current is very important. And motional EMF also important only. So, but first we'll discuss what is motional EMF, and thereafter what is eddy current also we'll discuss. Eddy current advantages. Clear? Okay, first question is from the DMI chapter is obtain expression for the induced EMF across a conductor which is moved in uniform magnetic field which is perpendicular to the plane of the motion. So question is obtain an expression for EMF induced in a EMF induced across conductor which is moving in a uniform magnetic field, perpendicular to plane of motion. Obtain an expression for EMF induced in across a conductor which is moving in a uniform magnetic field perpendicular to plane of motion. This is a question. So actually what is EMF? It is electromotive force, correct? So electromotive force, potential difference basically. Electromotive force is a potential difference, EMF. How this EMF can be induced means whenever electromagnetic flux associated with the coil changes, then we will get an induced EMF in a coil or induced EMF in a conductor. Whenever there is a magnetic flux is associated with the coil, a closed loop, it changes, then there is a induced EMF will come. From that induced current also will come, or it will induce EMF will be developed across the conductor or a rod. That is basic thing. That means to get an induced EMF, the flux has to be changed. So whenever flux changes, EMF will come, that we will calculate. Now for that, as per the question, there is a conductor which is moving in a uniform magnetic field, correct? So from that one diagram will make you see, we have magnetic field which is pointing perpendicular to the plane inward, like this magnetic field is there, uniform magnetic field is there. Into mark represent inward field is there. In this one, I am keeping one fixed frame of metallic wire. Okay. And this is something like length L. This is a fixed frame, wire frame. Now on this fixed wire frame, a conductor of length L, length L of conductor is sliding on this parallel wire. This is parallel wire is there, right? On that is sliding with a or moving, either this side or this side is moving. Clear? Now I am taking there is a wire or a conductor of length L which is moving with a constant velocity V in a uniform magnetic field like this. And I will make it as this is something like A, this is something like B, so this is something like C, and this is D. A, B, C, D is look like rectangular loop. A, B, C, D is a look like a rectangular loop. So I will consider this rectangular loop of length is L only. The breadth is considered something like this is X. At this moment, when the conductor of BC of length L is moving in a magnetic field at particular time, it is at X distance from this end. X distance from this end at this moment. Now you see, this conductor is moving like this. You see, like this is moving. Like this is moving like this. When this conductor is moving like this here, the ABCD rectangular area keep on decreasing. See, initially A, B, C, D, this is the area, complete area. Length into breadth, that is L into X is the area. But as this conductor BC in uniform magnetic field is moving like this, X decreasing, X decreasing. X decreasing means area also decreases. Area decreases means the field line which is associated with that area also changes. Field line changes means automatically flux will change, and that change in flux induces EMF in a conductor. Induce EMF in a conductor. Okay. So first we'll see. So for this, consider a wire frame of length L as shown, and a conductor of length L is moving in uniform magnetic field as with velocity v as shown. Okay. Now, as for this diagram, I can say the flux. Flux is magnetic field into area. So consider this magnetic field is B. Constant magnetic field strength is B. Then the flux is, or magnetic flux is, flux pi is equal to BA. Magnetic field into area. BA cos theta, but here theta is perpendicular to that area vector, and magnetic field 0 degree is there for parallelism. Sorry, parallel is there. So BA. So flux pi is equal to, I can write BA. B is only from this A is area of the loop, that is length into breadth. At this moment, I can write L into X. But from the Faraday law of electromagnetic induction, the induced EMF in a loop, or in a conductor is directly proportional to negative rate of change in flux. Negative rate of change in flux. So from Faraday, induced EMF E, that is equal to minus d pi by dt. Minus d pi by dt. So this induced EMF E is equal to minus d of dt of pi is what? B into Lx. B into Lx. B Lx. But from this, B is anyway constant magnetic field we consider. And L is the length, wo bhi constant hai. Or in that X only changing because of moving of conductor. When conductor BC is moving in a uniform magnetic field, so as per the diagram, that X is decreasing. So X decreasing means area changing. So in this one, I can say variable O is only the X. B and L is constant. So I can write BL is outside of differentiation. So that minus of B into L, d of dx dt, dx by dt. So from this, I can write it as B into L minus of dx by dt. I can write. See, from this, why I wrote that minus of dx by dt means dx, x is a distance. Dx by dt, time t is a time. So rate of change in distance or displacement as per the diagram. Rate of change in displacement or distance, it is a speed or velocity. Correct? So from this diagram, straight line only is there, whether it is distance or displacement, you call it is same only. So rate of change in displacement, we call it as it is a velocity, but here x is decreasing. X is decreasing, so that means velocity will get negative. Velocity will get a negative. So from this, I can write velocity as rate of change in displacement, that is dx by dt only. But why I'm saying it is decreasing means because your x is decreasing. So velocity will get negative. That means minus. V is dx by dt, minus of dx by dt. So from this expression, we got induced EMF BL minus of dx by dt. So in place of minus of dx by dt, I can write it as V. So that finally we got E is equal to minus, no minus, correct? E is equal to V L d minus dx by dt is V. BLV. This is the induced EMF across conductor moving in a uniform magnetic field. Simple question only. Just you need to draw a diagram with a simple wire frame we need to imagine. And in that a conductor of length L and which is from at x distance is moving a uniform magnetic field. Then flux BA, BL into X. X is changing here, so flux is changes. So d pi by dt, B and L is constant, we have taken out. Dx by dt rate of change in displacement, that is called velocity. But why I have taken that negative sign in velocity means here x is decreasing. So you can write, if you want, you can write here since x is decreasing. So we can write minus dx by dt as velocity. I replace that minus dx by dt as v. So we got E is equal to BLV. BLV is a motional EMF or simply EMF across the conductor. Is it clear, students? Very simple question. 2-3 mathematical equations are there. That is not more difficult. Yeah. Yeah, the next question from the same EMI chapter is, Describe the ways in which eddy currents are used to advantage, or simply we can say advantages of eddy currents. Question is advantages of eddy current. Advantages of eddy current we need to write. Simple. It's a pure theoretical question. So what is basically advantages of eddy current means? Actually, what is eddy current? What is eddy current? Eddy means circle. Eddy means circular. Circular currents or simply eddy current we can call. So when the eddy current will be developed, means, or circular current will be developed means, whenever a plate, a circular plate or rectangular plate or any kind of plate it is, any metallic plate or simple plate, whether metal or non-metal, a metal plate is oscillating in a uniform magnetic field, oscillating or in variable magnetic field you can say. Then due to this variable magnetic field, or when plate is oscillating, a circular current will be induces. Circular current will be induces. This circular current induces in a metal plate or plate, we call it as eddy current. Basically, if you see, there is plate is there here kept in a magnetic field, and this magnetic field we are changing. Magnetic field is changing. So whenever this magnetic field changes, so there will be a, like this current will be developed. Like this circular current will be developed in a plate. The plane of plate, the circular current will be developed. And this type of circular current developed in a plate, we call it as eddy currents. We call it as eddy currents. So basically these eddy current we can use in braking system in electric trains, that is called magnetic braking, we call braking system in electric trains, to stop the train or to decrease or to oppose the motion of the train. So we can use the concept called eddy current, or eddy current used as braking system for electric train. Next, it can be used to damping, electromagnetic damping we call. Damping means decreasing, oscillations or decreasing. Like, you know, pendulum is oscillating like this. So once you pull aside and release, after some time it comes to rest. So this kind of decrease in amplitude or change in amplitude of a oscillating body, we call it as damping. So in electro damping also we can use eddy current. Eddy current. Electro damping means, especially generally in a galvanometer we can use. The needle will be oscillate here and here to bring into rest the needle immediately or rapidly. For that, we'll use this eddy current concept. Eddy current concept. Then also we can use this eddy current in to making in alloys. To making in alloys by melting the metals. By melting the metal. To melt the metal, we know that which is required very, very high temperature. So to develop the high temperature in a furnace, so we'll use this eddy current. Especially we call induction furnace, we call. Induction furnace. In that also we'll use induction furnaces are used to develop high temperature to melt the metal. So that can use the concept of eddy current only again. Last one, there is a in electric meter. In electric meter also we can use. You know, in electrical meter there is a disc will be rotated in the meter. So this rotation of disc is possible due to the eddy current. due to the eddy currents, right? So these are the main advantages of eddy currents, right? So first advantage is magnetic braking. Magnetic braking. Magnetic braking. What it mean by braking means trying to stop the motion. So what is magnetic braking mean? So generally this braking system, eddy currents used as braking system in electric trains. Generally in the electric train there will be on rails, there above the rails they kept the electromagnets, and when these electromagnets are activated, there will be eddy current will be produced, and this eddy current try to oppose the motion of train, that means it is act like a brake. That's the reason it is called brake, eddy current or magnetic braking we call. What is that? Electromagnets are kept above the rails when they are activated, eddy current produce. And this eddy current produced and which oppose the motion. This is first advantage, magnetic braking. Simple, because in electrical train braking system has electromagnetic or magnetic braking system. And on above the rails electromagnet will use, and when they are activated, so eddy current will be developed, and these eddy current will oppose the motion. Clear? Next. Magnetic damping. Magnetic damping. Damping means decreasing amplitude. So generally this concept will used in a certain galvanometers. The coil in a galvanometer to bring rest rapidly. So this concept will be used. So generally in galvanometer, coil in galvanometer to bring the coil to rest, eddy current will be used. Generally the fixed core of the galvanometer as non-magnetic metal will be present. So whenever magnetic field is generated, and this produces an eddy current, and this eddy current will oppose the motion of the needle. So oppose the motion of the needle so that which is deflected something, and immediately it will comes to rest. So rest, it will come to rapidly, it will comes to rest. Next, after magnetic damping, Induction furnace. Induction furnace. Generally, this furnace used to develop high temperature by using the concept of eddy current. By using the concept of eddy current. Generally, it is used to make alloys by melting metals. And we know to melt the metal, we required high temperature. We required high temperature. This high temperature can be developed by producing eddy current around these metals. Generally, in this induction furnace, in furnace or induction furnace, metal is surrounded by coil. Metal is surrounded by coil, and the eddy current, when alternating current flows through coil, produce eddy current. Eddy current, and which used to produce high temperature. Okay, this is induction furnace. The last one is basically electric meter. Electric meter. That is, so there is a disc will be present in electric meter. The shiny disc will be present, it will rotate. So generally, to rotate the disc in electric meter, eddy current concept only will use. Okay. So generally, to rotate the disc in electric meter, eddy currents will be used. So generally, when high frequency of alternating current is allowed or passes through the electric meter, then eddy current will be generated, and that try to rotate the disc. Okay, simple. We can write one line is, when high frequency AC current flows, eddy current will produce, and this will rotate the disc. And this will rotate the disc. Clear now? So advantages of eddy current: magnetic braking system, magnetic damping, induction furnace, electric meter. These are the four main advantages we have. And briefly, each and every advantages, briefly 2-3 lines you can write. Then this is complete answer for advantages of eddy current. So today we'll stop here only. So from these from the electromagnetic induction, 2 questions we have learned. And tomorrow we'll study the another chapters, SAQs. From this chapter, SAQs of advantages of eddy current and motional EMF. These 2 questions before this one and this one are very important and simple questions only. This is pure theoretical only. Before also little bit mathematical equations are there, but there's also simple mathematical equations. Clear? Right.